Hello, I'm Prathamesh Ternikar. I work from Armstrong International's office in Michigan, and I belong to Armstrong's global team of utility system engineers. In this role, our job is really to help Armstrong's customers to decarbonize thermal utilities while improving energy efficiency, safety, productivity, and reliability. Before we get ahead, I would really like to thank Renewable Thermal Collaborative for giving us this opportunity to really present some of our learnings that we have had in this journey of decarbonization. Over the next 25 minutes, I will present a case study, which is a summary of not one, but many decarbonization and energy efficiency studies that Armstrong's team of utility engineers have conducted over many decades. To maintain confidentiality, I have masked specific details of the projects with hypothetical numbers and flow rates. And I'm hoping that with this approach, we'll be able to freely share the technologies implemented, the methods adopted, and the results achieved without digressing into the proprietary manufacturing process and business practices. In case you find any similarities, please consider it as a rare coincidence. Many of you who are listening and work in thermal energy field might have heard about Armstrong International. Some of you might also be aware of Armstrong's culture of storytelling. So when things get too complex to explain, storytelling is our go-to method. And continuing with that tradition, instead of graphs and charts and calculations, I will be telling you a story about a plant's journey to decarbonize. It's going to be a very light session, so it's best enjoyed if you just relax and maybe even grab a drink suitable to the clock in your time zone. The story that I'll be telling you is about a chocolate plant. The name of this plant is Skywalker, and it's in Star City, Texas. So this Skywalker plant decided to decarbonize its manufacturing. Well, that's not the complete truth. What happened is Skywalker's corporate office, which is in the town of Turku in Finland, they own many food production facilities in many countries. So Skywalker has always been a leader in sustainability. So it set itself a very ambitious goal to decarbonize all the manufacturing plants globally by the year 2030. So the same goal was given to the Skywalker chocolate plant in Texas. Upon hearing that Skywalker Corporation is looking for partners to help them achieve the target carbon reduction, Armstrong's team made a presentation to the C-suite at corporate office in Finland. We presented Armstrong's approach of optimize, minimize, and decarbonize, meaning optimizing really helps improve thermal utility system efficiency. Minimizing challenges the current level of thermal demand, and by these two steps, we serve to eliminate about half of the current thermal demand, which simplifies the final step, which is of decarbonizing the thermal generation. Each of these steps have many milestones or mini targets, which help us to reanalyze on the standing and correct ourselves. Skywalker corporate team, they really liked this method, and the reason was it was closely in sync with their internal method, what they call it as reduce, reuse, and replace. So we were tasked to begin with the first chocolate plant, which is here in Star City, Texas. So this is how we landed at this facility, and this is how the story begins. The first step, as we said earlier, is optimize, and the goal is to improve thermal efficiency. The first milestone in this step is what we call it as a thermal assessment. So myself and my colleague Navena, we visited this plant before the pandemic. So, we were able to have a nice in-person discussion to introduce Armstrong, but also to get to know the facility, the people, and the challenges which were beyond the obvious decarbonization target. The biggest objective behind this visit was to make the facility understand that this is once in a generation opportunity to undo all the wrong that may have forced their way into the plant due to production time or maybe financial constraints. So when we visited this plant, we saw that the primary sources of energy feeding thermal demand are natural gas and electricity from grid. Natural gas was used to generate steam, and steam was used to make hot water at multiple locations in the plant. Steam was also used for air conditioning. A small amount of steam was used for heating product in batter unit. Hot water was generated at three temperatures, 110, 140, and 195 degrees Fahrenheit. It was used for product heating in tanks. It was used for tracing praline and fats, and it was also used for CIP or cleaning process. There are four water-cooled chillers, each of 20-ton capacity, that generate chilled water for product cooling. The chiller and air compressors are water cooled. So a central cooling tower plant recirculates water to equipment. One of the two steam boilers have economizer, which can recover heat from stack, but a significant quantity of low-grade waste heat was available in form of cooling water or wastewater. Some of the challenges that we identified at this facility are shown here. I'm quite sure that the listeners who are in charge of utilities will have at least three of these challenges in their plants, irrespective of the product that they manufacture or the facility they operate. No metering of utilities is again a classic. There are many plants and facilities that don't believe in metering, but have steep energy and carbon reduction targets. Without metering, there cannot be a baseline, and without baseline, we don't have a starting point in journey of decarbonization. The other aspects mentioned on this slide are also quite obvious, but often neglected. Post-thermal assessment, we started with a measurement campaign with ultrasonic flow meters and data loggers to measure flow and temperatures of all the utilities. Though there was a lot left desired on utility metering, the chocolate plant had excellent metering when it came to raw material and process flows and of products. So we were able to collect quality process flow data from plant instrumentation. The collected data helped us to create a heat map of the facility. Now, thermal mapping of a site, it not only identifies heat sources and heat sinks at different temperature level, it also quantifies them and really determines the availability according to the time and location of the facility. So in this thermal mapping study, we predominantly use Excel-based tools that are developed in-house. There are many softwares available to do this too, but the software itself will not go and identify sources and heat sinks. So to identify those, we have to have a full understanding of the facility's processes and its dynamics of operation first. So different heat sources and sinks will have their specific load profiles. So in this phase, we use average annual values of the most important streams to indicate the potential, knowing it very well that adjustments will be required to balance the overall system at a later stage. So this modeling can be best done in a tool like Excel, which has a typical structure that can be developed on the go. So in the next phase of detail engineering, where equipment has to be sized, the softwares can come handy to find the exact sweet spot in pinch. And we do that by considering the historic load profiles. Based on the heat mapping to optimize energy use, we did pinch analysis and we designed new heat exchanger network that included additional storage tanks, heat exchangers, and temperature and flow control valves to ensure a uniform flow rate and temperature to users. We also identified locations where temperature of heat sources was lower than that of heat sink. For example, chilled water return coming from the plant was at 53 degrees Fahrenheit, whereas the lowest hot water temperature requirement for heating in tank was 110 degrees Fahrenheit. So for applications like these, we designed heat pump. Very quickly, I would like to take you through one application of heat pump. In this case, heat pump extracts heat from chilled water returned from plant, that it cools the chilled water before it goes to chiller for further cooling to required supply temperature. So what we do is we put a heat exchanger, technically called as an evaporator, that cools or pre-cools the chilled water return and heats the refrigerant before it goes to compressor. In a compressor, as we know, the refrigerant is compressed, thereby increasing its pressure and temperature. So this high temperature refrigerant then passes through another heat exchanger called as a condenser, where it releases that heat, and that heat is picked up by hot water return coming from the facility. So by installing a heat pump, we can raise the low grade waste heat to medium grade usable heat, which can then be used for process heating. In this particular case, for a 34 kilowatt electricity input to compressor, we extracted 100 kilowatt or 340,000 BTUs per hour of heat, and we also reduced load on chillers by 70 kilowatt. So in a nutshell, for a 34 kilowatt input, the total heat output is 170 kilowatts. So the overall coefficient of performance of COP of the system is 4.1. And now, since at Star City, Texas, the gas to electricity prices at this facility in particular was less than 3, not only did we decarbonize the entire gas to steam to hot water network, but we also had a positive return on investment. Of course, we all know that heat pumps like these should run on renewable electricity, and they should use safe, environmentally friendly refrigerants. What we also do wherever required is design heat pumps with a standby compressor. So that acts as a redundancy and ensures 100% utility availability. A similar heat pump network was designed on cooling tower water, but considering the paucity of time, I will not be discussing that project. However, what I will develop upon is digital mixing valves that are installed in the hot water loop after the storage tank. A complex thermal demand of flow and temperature cannot be met by individual heat pumps. So to cater to that complexities, a mixing valve helps us to deliver hot water at precise temperature required by the process, while the heat pump can operate at its best COP delivering temperature set point. Another interesting project that we did at Skywalker was replacing hot water and steam used for heating, ventilation, air conditioning. Skywalker plant has close to 25 AHUs that maintain humidity between 45 to 65% at various zones depending on the product manufactured. Through a heat pump network, we delivered a chilled water and hot water for heating and cooling loops of the AHUs. But we have discussed how that happens already. So we'll skip that part and move to the interesting part of this project, which was introducing adiabatic cooling into AHUs that resulted in complete elimination of steam for humidification. Adiabatic process, as we know, is a natural and extremely efficient process. Adiabatic humidifier, it converts liquid water to water vapor by the using adiabatic process. Dry air, it is passed through a corrugated wet bank of cell media, which is made of non-organic wet fibers. So the humidifier uses sensible heat in air to evaporate water, which cools and humidifies the air. Adiabatic process consumes no electricity, making it an ideal choice to reduce energy and carbon footprint. If you are closely following me, you might have realized that by now, the most of the steam that's used at Skywalker is used at temperature which is less than 200 degrees Fahrenheit, except for one process which is of batter preparation, where steam is used at 5 psig for heating kettles. Now, even by optimizing steam and condensate loops and by implementing best-in-class maintenance programs for steam traps and insulation, the overall efficiency of steam and condensate system at Skywalker plant could only reach 80%. So we started to work on alternate ways on meeting this demand. What we ended up doing is, again, we designed a heat pump that could deliver steam at 10 psig, corresponding to 239 degrees Fahrenheit. The COP of this system was not as great as some of the earlier applications that we discussed, but even then, considering both heating and cooling loops, the overall efficiency was still 3 times better than a steam system. So by undertaking this optimizing step, we were able to reduce energy demand by 55%. It also helped us to reduce operational expenses by 35%. All the major projects identified had a payback which was less than 10 years, which, though debatable, is exciting considering the decarbonization potential that it has. The paybacks are, again, very geography specific. Now, the same projects, if they were done in Europe or in countries where they have high gas prices, the same project would have a payback which is less than 3 years. So this stage of optimizing thermal loads typically helps us to reduce carbon intensity between 50 to 60%, and in our experience, the OPEX reduces by 30 to 40%. One thing to note is that decarbonized thermal systems are more dynamic than existing oversized one-directional thermal utility networks. They require more data points to measure flow, temperature, pressure, and other key parameters. The latest generation of batteryless energy harvesting sensors collect such data at a lower cost. Artificial intelligence software will be increasingly used to manage dynamic controls that are required to maintain a balance between thermal demand and supply. That brings us to the next step, which is minimize. This step prevents oversizing of future decarbonized thermal utilities. Though it's a next step, it's a simultaneous step with optimization. So we already start on minimizing while we are working in an optimized phase. We all know that the latest state-of-the-art process and HVAC equipment optimizes heating and cooling temperature set points that are required to deliver the same output. We worked with OEM suppliers of Skywalker, and we identified latest technologies in manufacturing process. The new technology that was adopted or recommended for adoption is actually a replacement to end-of-life equipment. So that really helped us to replace some of the old technology. And we also worked with process engineers, and we really narrowed down the optimal temperature set points. So once the set points were lowered, we went back and we redesigned the heat exchanger network to provide hot water at much lower temperature. So generally, a heat pump has higher COPs by reducing the temperature difference between condenser and evaporator. So minimizing temperature for process helps us improve COP of heat pump, which in turn helps us to reduce the operational expenses and increases the returns on investment. Due to complexity of the process and the high investment cost, though it is end of life, the return on investment is higher than some of the measures that we had identified in the earlier stages. However, it is worth noting that at least in Skywalker's case, the ROIs are still positive, which in itself is not a small achievement. Based on the numerous studies that Armstrong has conducted, typically improving process equipment and process set point can help us reduce carbon impact between 10 to 20%. And the measures also help us to reduce operational expense by 10 to 20%. Since most of the capex is for end-of-life equipment, the investment decisions are obvious and sometimes faster than some of the other projects in the decarbonization journey. So as we have seen at Skywalker, the overall optimizing and minimizing serves to eliminate more than half of current thermal demand. This really simplifies the final step of the roadmap, which is decarbonization of thermal generation. This is the most complex phase because we have to look into a crystal ball and make assumptions on what the future product and fuel mix will be. Skywalker plant has a target to source 100% sustainable and traceable cocoa beans. Now this, at least in the short term, will result in change in raw material quality. This obviously will lead to a deviation from present specific energy consumption. The same holds true for electricity. Though the current renewable electricity rates are only 3% higher than fossil fuel electricity, the utility is unwilling to sign long-term power purchase agreements. This introduces higher risk factor in energy and carbon modeling. The Skywalker sales team provided us with product mix and demand projections for next 10 years with high confidence levels. So we were able to use these data parameters and put them into a model for energy and carbon scenario for the various options that were identified. The modeling, as we discussed earlier, is done by blending our in-house Excel-based models and third-party modeling softwares. Unlike the projects that were identified in optimize and minimize step, decarbonization projects usually lead to increase in operational expense, and that's just because of the inherent nature of some of the project. The CapEx or the capital expenditure requirement too are higher than energy reduction, energy efficiency projects. As an end deliverable, we developed various scenarios to decarbonize the residual energy demand. A few of the options that made to that list are shown here. The widely applicable technologies and methods are easier to adopt and implement, with optimizing the thermal loads by using pinch analysis and heat pumps and common energy efficiency measures. Skywalker can reduce their thermal load by 55%. The widely available technologies for decarbonization are electrification of hot water generation, shallow geothermal, and carbon capture. These are well-established technologies and can be implemented with relative ease as compared to some of the other technologies which are complex to adopt or they are just too geography specific. So at this Skywalker plant, more than half of carbon footprint, as we know, was reduced by optimizing and minimizing. The remaining half or less than half was met by decarbonizing the energy sources. The process utility changes like de-steaming and custom design technology alternatives like heat pump and adiabatic cooling help to reduce energy demand substantially, leaving only half or less than half of current thermal demand that needs to be decarbonized. We strongly believe that thermal mapping and optimizing is really a no regrets first step for building organizational momentum and confidence in this journey towards decarbonization. So like we all know, there is no one solution that fits all. Every plant is unique, every process is unique. But by following a disciplined three-step repeatable process of optimize, minimize, and decarbonize, we can not only achieve the decarbonization goals, but we can also use this opportunity to reduce our energy consumption, improve safety, improve the productivity and reliability of the equipment and the operation that we run. So if this presentation has triggered any queries, please go ahead and ask them now, or you are most welcome to visit Armstrong's virtual room, where we can have a more detailed discussion on not just the technologies, but also the method that's followed for the decarbonization. With that, I thank you for your time and have a great day ahead. Thank you.